Hello everybody and welcome. My name is Chad Heffernan and I'm the inventor of a new valve design called the Eclipse Valve, and I'm going to introduce you to it as briefly as I can here. It's important to note that I have patents that have now been approved in the US, China, and India, and it is protected until 2041. Alright, so we're going to talk a little bit about how I came up with this idea and introduce you to the problem that many of you may not even know exists. The market research that I've done is very extensive. I think you'll find any other invention, you'll be hard pressed to find somebody that's done more market research than I have. Interesting stories there. I'll introduce you to the technology, including how it works, and then we'll conclude with what the ask is and what I'm looking for from you. All right, so let's talk about the problem. There are two specific valve designs that are very prevalent in the industry for controlling flow, and one of them is the globe valve. So anywhere you need precise flow control, you'll typically specify a globe valve. But the globe valve has inherent problems. You've got a turbulent flow path, so that leads to cavitation within the device itself and everything downstream of the valve. You have very heavy and expensive actuators required to control the flow, and then you also have a large inherent pressure drop. Now that's something I'm going to revisit a little bit later when we talk about my design. But then you also have the lack of inline serviceability. So you want precise flow control, you have to use a large, heavy globe valve with large, heavy, expensive actuators in order to accomplish what you want. But if you have a failure or a valve that needs servicing, you got to remove it. The other design I'm going to talk about is a ball valve. So specifically characterized ball valves that are designed to control flow. Now, the ball valve also has some inherent flaws, even if you're looking at characterized ball valves for flow control. So you've got the turbulent flow path, same thing that you have within the globe valve. So again, that leads to cavitation, damage downstream, vibration, noise, and that cavitation can cause damage to the valve itself and basically cause the valve to eat itself. You require a lot of torque, so there's a lot of surface area in that ball valve, in that socket, to be able to move that valve 90 degrees. You do have very poor flow control. Now, you can get good flow control with an expensive, highly machined, characterized ball valve, combed ball valve, those kinds of things. But it's still ultimately trying to mimic what a globe valve can do when it comes to flow control. Now, the flow is also directed to the sides of the piping and the interior walls of the sealing surfaces of the ball valve. So when you have that turbulent flow path that's introduced to the interior walls of the piping, the damage that can cause to the interior walls of those piping can be significant. And again, you have a lack of inline serviceability, right? They have to be removed if you need to service or replace a valve. All right, so the market research. So this is really interesting. I don't have an engineering background. However, I had some neighbors that were into venture capital, and they introduced me and brought me on board to a company that had invented a new type of control valve. And so I ran sales and marketing for them. I set up their distribution network. And the premise of this valve was that it was a full bore control valve, like a ball valve. However, it was much more precise, and it could also be a very good stop valve. So I was able to sell that to pretty much every major oil and gas company, chemical manufacturers, aerospace companies, military branches worldwide. So I found that there was a huge appetite for a full bore control valve. However, it was not inline serviceable. It's expensive to manufacture, required many moving parts and pieces, and ultimately that company did get acquired. But I'm looking to do the same thing and introduce a few new features, as well as make it more compact and less expensive. So the applications are very broad. For a full bore control valve, I'm thinking, for steam control, for fluid and gases control, for fuel control, temperature loops, just about anything that you would typically use a globe valve for. That's what I want to go for. And anywhere you would specify a characterized ball valve, I think I've got a new technology that's going to be better than that. So the manufacturing expense was also something that was very near and dear to me, because in order for something to be profitable, it has to be inexpensive to manufacture. And so the design that I've come up with is very simple, very inexpensive to make, and requires some machining, but it can be mostly done with investment casting. The inline serviceability is a huge thing. So instead of advanced replacement, you can service and replace the innards, the working components of an Eclipse valve in less than 1 minute. This means that they can be welded into place and you still have the serviceability. All right, so here is my introduction to the Eclipse valve. So what you see there is a picture of my prototype that I made on my 3D printer. I've got the dimensions down. I've got the mechanism working perfectly. In fact, I have it right here. And let's go. So how does it work? It's pretty simple. So you have two bevel gears that are driven by a beveled pinion gear. And when you put those into the body of the valve and have a cover with valve stem on top of it, 6 bolts will hold this entire mechanism together. So that means that not only is it very simple, we actually have very few parts to manufacture, but the way that it works is that we can sell the valve, and if you have extensive service or extreme service valves that need constant attention, like in precipitated calcium carbonate flow or something like that, you can replace the innards on this valve. And there are some valves out there in such extreme service they need to be replaced multiple times daily. This would save a significant amount of expense just by being able to replace the interior parts. If we're looking at it from the top, the pinion will drive both the plate gears, and I know a lot of you are thinking, well, how does it seal? So first and foremost, I wanted it very simple to seal and inexpensive. So we can use off-the-shelf standard O-rings. And what it looks like from a perspective, you just have a channel that holds the O-ring into place. And then that way, once it goes onto the interior surface of the body of the valve, that seals that part. In addition, you have O-rings in between here, and it's difficult to see from this picture, but you've got I put a clear plastic case over this, so you can see that these standard O-rings are able to seal the fluid flow from getting into the interior workings of the valve and into those gears. But you also have an O-ring on the other side, and in this manner, we're able to perfectly seal the valve so that we have a wide aperture and a full close. And then these 4 O-rings or more, if you wanted to do a higher pressure application, are used to seal off the flow and shut it down. If we're looking at it from this perspective, we can actually use bands, rubber band O-rings or elastomer of some sort. And when they go together, it looks something like this. So the seals would go on top of these plate gears, and then the plate gears would go into the ring, and now we have a sealed system that is able to be driven. So here's what the entire mechanism looks like in my 3D rendering. And here is how the entire assembly goes together. What's great is when you have Eclipse valves in place, you can stock a number of these, right? So again, in those extreme circumstances where you have difficult applications that are hard on valves, you've got the capability of keeping these on the shelf. From a manufacturing and from a revenue standpoint, it's like we're selling the brakes and we're also selling the brake pads. So it's designed to last, it's designed to precisely control flow, but it's also designed to be inline serviceable and allow continuing revenue from the service parts that can be readily housed on the shelf. Now this is what was interesting when we did a computational fluid dynamics analysis of what the valve would look like in service. We found that it was very precise flow control from 10 to 20% opening. So this is important in applications like steam control, but if you look at it, it's a very logarithmic type of flow. It's very similar to what you would get with a globe valve. So being a full bore valve, P1 is equal to P2. So if we look at this in comparison to a 4-inch globe valve, we know that the pressure drop inherent in a globe valve is not equal to that of an Eclipse valve. This is a 100% full bore, and it actually acts like a full piece of pipe when it's open full. So the flow from a 1-inch globe valve can equal the flow of a 4-inch, of a 1-inch Eclipse valve can equal the flow of a 4-inch globe valve. Now we also know monetarily, if you want the performance of a globe valve, something that is the size of your fist with a small actuator the size of your fist is going to be much smaller, lighter, and less expensive than a 4-inch globe valve. We also know that the piping required, now this is important, when you have skids that are comprised of 4-inch piping and 4-inch globe valves that could be made much smaller with a 1-inch Eclipse valve and 1-inch piping, we're again making things lighter, less expensive, and more compact, also more shippable. So you think about the costs of putting skids on rail cars. When that skid can be much more compact, you're able to save money on the shipping. All right, so we know the weight is also a big factor. So you think about things in aerospace where they're typically using ball valves for fuel inlet valves and things like that. We can do the same thing but allow precise flow control. So we know that the weight between these two, this comparison of the globe valve and the Eclipse valve, it's going to be much lighter. Now the actuation mechanism, this is a 180-degree actuated valve, not a 90-degree. And the reason is I had to use 180 degrees to get the right gear ratio in order to allow the face-to-face dimensions to be the same as a 1-inch ball valve. So in order to get this valve to market, it's designed to be bolted in place of where there were existing 1-inch ball valves. And the connection can be flanged, it can be welded, it can be threaded, MPT, whatever. But the actuator can be much, much smaller than those of globe valves. Now, if we're looking at the actual size comparison, this is to scale. This is a significant decrease in size. All right, so we know that there are multiple applications for this. I've seen this. The appetite out there for a full bore control valve is palpable, and it is vast. It's designed to retrofit. So in cases where there's a 1-inch ball valve that's doing control, either characterized or not, this is a much better solution. It's built for manufacturing. So again, we've got the 3 pieces that we can sell, and then you just have a body and a cover with a valve stem. So very few moving parts and pieces, very easy to manufacture, and very inexpensive. And the continuous revenue model. So the inline serviceability is huge. The ability for somebody to maintain lines that have control valves that are continuously failing or need service, when this can be rebuilt in less than 1 minute. Again, keeping service parts on the shelf and having this valve put through its paces and extreme services is where we're looking. World changing. So here's the thought. So I was working with a pilot plant for a major oil and gas company back when I was working in the other valve company, and what I discovered is that they're trying to use very tiny, like 1/4-inch swage lock ball valves for control. And ultimately, the problem with that is they didn't control very well, so they didn't get the identical response that this pilot plant is trying to simulate out in the fields where they're actually doing the refinery, oil refining. So if you have the capability of putting something like my valve in place and simulate more lifelike performance of a globe valve in larger, in real-world full-size applications, that's going to equal money. You're going to be able to more efficiently and effectively recreate what the flow is going to look like, what the P&ID is going to look like in the full-scale sense. I also think, if we're introducing a new valve design to market, it is world changing. You're going to have, if you have the ability to specify this valve into any place where there was a globe valve, you know that your skids are going to be much smaller, much lighter, much less expensive, use less energy, be more shippable, and then the inline serviceability is going to make manufacturing very inexpensive for companies. It's going to make chemical refining, oil and gas use, aerospace use, all those things are going to be less expensive to operate. So with that being said, I am looking for somebody to acquire or license the technology to. You have my contact information here on the screen, so anybody interested, please let me know. And I appreciate you joining me for this this long-winded introduction to the Eclipse Valve. Have a great day.